Hey YouTube, welcome back to Intuition. In today's episode, we're going to continue our Pharmacokinetics review and Naplex review. Specifically, we're going to answer questions about drug abuse and drug potency. Stay tuned. Okay, so in today's video, we're going to answer 3 questions. And these are good concept questions that will hopefully refresh your memory of some pharmacy concepts or teach you something about pharmacy and the potential for drug abuse. With that said, let's dive into these questions. Question number 1. Question number 1 states, the above graph are dose response curves for 3 different formulations of drug X. Which formulation of drug X would be most susceptible to drug abuse? Okay, very straightforward question here. There's a certain drug X, and a pharmaceutical scientist has made 3 different formulations of this drug, right? So it's the same drug, but they're 3 different formulations. These 3 different formulations result in 3 different dose response curves. Now we're being asked to pick out the dose response curve that would most likely lead to drug abuse, assuming that this is a potentially addictive medication. So let's use our intuition and try to figure this out. If we have different formulations of the same drug and we're trying to figure out which one would most likely lead to drug abuse, what's one factor you can think of that would be a contributor to drug abuse? Well, I would probably think that the drug with a very high response rate, a drug that causes a very high response, would be the drug that would be a good candidate for potentially being abusive, because the patient really gets a big kick out of this medication. So which one of these drugs has the biggest kick? Looks like drug A, right? But not so fast, because what other factor can we think of that would contribute to drug abuse? Think about it. We live in the era of fast food, instant coffee, likes on social media. Why are we addicted to those things? A big factor for abuse and addiction is instant gratification, a response that occurs quickly. And it turns out that that is the biggest factor for predicting drug abuse. Now, when you look at these 3 graphs, which one gives the fastest response? Drug B. Drug B reaches its maximum response faster than drug A or drug C. And that would be the answer. The answer would be formulation B. So what does that tell you? Patience is a virtue. This was a good one. Let's go on to question number 2. Question number 2 states, in the graph above, the maximum response to drug X is twice that of drug Y. Which of the 2 drugs is more potent? Now we're asked about potency. What kind of question is this? This is a definition question, because you need to know what the word potency means. You might think that a potent drug would be a strong drug that really causes a huge response. And we're told in this question that drug X has a response that's twice that of drug Y. So you might be like, well, drug X must be very potent. But that would be incorrect, because that is the incorrect definition of the word potency in the world of pharmacy. In pharmacy, a potent drug is a drug that causes a response at a very low concentration. Now, looking at these 2 graphs, we start to dose these drugs and we see that the first drug to cause a response is drug Y. It's a very low response, but it causes a response sooner than drug X. We have to continue to increase the concentration of drug X beyond that of drug Y before we get a response to drug X. But once we do get a response to drug X, it's a very high response. But that's not the definition of potency. Potency doesn't care about the level of response. It cares about the concentration at which you receive a response. And because we received a response for drug Y at a lower concentration, the more potent drug is drug Y, not drug X. All right, so answer is B. That's a good concept question. I enjoyed that one as well. So let's move on to question number 3 now. Okay, question number 3. The oral formulation of a new drug dosed at 100 milligrams leads to a total exposure of 0.15 milligrams times hour per milliliter. If the bioavailability of the drug is 80%, what is the half-life of the medication? Assume that the volume of distribution is 6 liters. Round to the nearest whole number. Okay, so this sounds like a math question. My favorite. Okay, so with this question, we're told that there's a drug and it's being dosed at 100 milligrams, but only 80% of the drug is absorbed. 80% of 100 milligrams is 80 milligrams. So basically only 80 milligrams out of the 100 milligrams is absorbed. We're being told that this 80 milligrams leads to a total exposure of 0.15. Now, what is exposure? Exposure is basically the area under the curve for the concentration versus time curve. And the area under the curve, or the exposure, is basically the average concentration that occurs throughout the distribution of the drug times the total time that the drug spends inside the body. So from the time of absorption to the time of elimination, that total time is being multiplied by the average concentration throughout the distribution and therapeutic journey of the drug. That's drug exposure. This is a very simple equation that links the amount of drug absorbed and drug exposure. And that equation is that the amount of drug absorbed is equal to the drug exposure, or the area under the curve, times the drug clearance. Clearance is the volume of blood that is cleared of drug per unit time. The clearance times the exposure will give you the amount of drug absorbed. The total amount of drug eliminated is the total amount of drug absorbed. Okay, so now that we have our equation, we can go ahead and solve for the clearance. The amount of drug absorbed is equal to 80 milligrams. The AUC, or the exposure, is 0.15. So we divide both sides by 0.15, and that gives us our clearance. Now that we have our clearance, how do we get the half-life of the drug? Remember, what is clearance? Clearance is the volume of blood cleared of drug per unit time. So if we divide the clearance by the volume of distribution, then we'll get the fraction of blood cleared of drug per unit time. And the fraction of blood cleared of drug per unit time is going to be equal to the fraction of the total drug cleared per unit time. And what does that equal? That is equal to our rate of elimination constant. So that equals our K. So K equals clearance divided by volume of distribution. To solve for our K, we divide the clearance by the volume of distribution, but we want to make sure that we're working in the same units. We have our clearance in terms of milliliters per time, but we're given the volume of distribution in terms of liters, so we want to convert the volume of distribution to milliliters, which will be 6,000 milliliters. And then now clearance divided by volume of distribution equals K, and that gives us a K of 0.088. So now that we have our K, we can solve for our half-life. If we recall the equation from last time that we solved for, minus the natural log of 1/2 is equal to the natural log of 2. So the natural log of 2 divided by K is equal to the half-life. Because remember, the half-life corresponds to where the drug concentration is cut in half. And that's where the 1/2 comes from. But because it's negative log of 1/2, we can convert that to the natural log of 2. So the natural log of 2 divided by the elimination rate constant should give us our half-life. And when we solve for that, we get approximately 8 hours. And our answer is C, 8 hours. Easy, okay? So I hope that makes sense for you guys. If you have any questions, go ahead and leave it in the comments below. If you're new to this channel, go ahead and hit the subscribe button. Give us a like. We release videos every Wednesday here on this channel. And we cover a wide range of topics. Right now, most of us are studying for the Naplex, so I'm covering a lot of Naplex videos. But any other topic that you're interested in, just go ahead and let me know. And stay tuned. Go ahead and subscribe to the channel and become part of our family. So I look forward to seeing you guys next week. See you on Wednesday. Bye-bye.